for the afternoon talk. We have Bruno Loureiro talking about learning features with two-layered neural networks, one step at a time.
Okay. Hello, everyone. Let me start by thanking the organizers for organizing this amazing workshop and for inviting me here. So, yeah, I'm Bruno. I am coming from École Normale Supérieure in Paris, in CNRS. And so thinking about, like, on a high level, how to describe the talk, yesterday I was looking at the program of the conference, and I think that's a perfect kind of short abstract, what we're going to be trying to do today. So we're going to be trying to model randomness in neural network training using random matrix theory and understanding matrix value random process that arrive doing that neural network training. Okay, so this is going to be a little bit on 3 works, 2 of them which are already out. The first one is essentially like concentration bounds and inequalities for this problem. The second one is exact asymptotics, so based on some heuristic methods from statistical physics, like the replica method. And the third one, which is not out yet, but should be out soon, is like using random matrix theory to prove these results. So yeah, so like coming back to Michael's talk in this morning, I'm kind of in the 1% of people who care more about theory than theorems. So I'll try to flesh out for the ones of you who are more RMT geeks, like what are the main ideas, but that's not going to be the main part of my talk. Okay, so what is the high-level motivation here? We want to try to understand, just like some of the previous talks, feature learning. We want to understand what this ever mean. That's usually one thing if you Google like why deep learning is amazing. People are going to say, oh yeah, because it can adapt to the data and learn features. But how to even start defining this mathematically, right? So that's what we're going to be trying to make sense in this talk. This is going to be in very simple models where we can give precise answers to what feature learning means and how does it help in generalization. Okay, so that's going to be the goal. We're going to make a lot of assumptions. We're going to be trying to be precise about what features are bringing respect to not learning features. So in the menu for the talk today, we are going to be starting at initialization, so no feature learning, kernel methods. We're going to be recapping a little bit of the results in the literature about that. Then we're going to be considering just one single gradient step. So we're going to be asking, after one single gradient step, what can you learn, under which conditions you learn, and how what you learn impact the generalization error. And then I just want to flesh out, like in the third paper, there are also results for what happens when you do a few steps, but that's not going to be covered today. So if you are interested, I'm happy to go through it offline. So today, just initialization and one step of stochastic gradient descent. Okay, so let's get going. We are going to be assuming that we have some training data, so we are doing supervised learning. This data is sampled IID from some distribution. So my y's are connected to my x through a target function. And we're going to be assuming throughout this talk that my input data is Gaussian, so it's isotropic. That's the most important part. And my noise is also Gaussian. So it's a very interesting question, what happens when things are not isotropic, but that's not for today. Today we're assuming things are isotropic. So in some sense, all the structure of the data comes from the likelihood y given x. X itself is unstructured. You won't learn almost anything by just looking at x. You really need to learn y given x. We're going to be looking, as the title of the talk suggests, at two-layer neural networks. So that's my notation for two-layer neural networks. I'm going to be working on this kind of NTK scaling because I'm going to be talking about kernel methods at initialization. But then we're going to be seeing how we're going to learn features on the top of that. I have my input data lives in d dimensions, so that's the important thing about this slide. I have p hidden units, and I have n samples. So these are the 3 quantities that matter in this talk, n, p, and d. And we're going to be considering just standard empirical risk minimization. So since we're doing regression, we're going to be considering the square laws and potentially some regularization, which I'm going to specify as we go on in the talk. But for this slide, just setting up some notation in the most generic setting, we're going to be considering, and then we're going to be specializing in some classes of target functions, in some class of regularizations, and so on. So as I said, we're going to start with initialization. So what do we know about initialization? This has been studied a lot. So if we just now consider fixing the first layer weights at initialization, like any initialization you like, typically you can take like to be something in the sphere with the right normalization, and then we just train the second layer. So what can we learn by not training the first layer, by not learning features? So this is what is known as the random features model. It has been introduced first in the context of approximating kernel methods, but due to the results on Gaussian processes and neurotangent kernels, some people like to study this model as a proxy also for what neural networks can learn in the lazy regime. You can think in this model the way you prefer, but this model is nothing but a kernel method, which is a finite p approximation to a kernel method. So the question we are interested here is, given a kernel method, what can we learn when the data is isotropic at a given p and n? So this has been the subject of many works over the past few years, and including works of people in the audience. So yeah, I mean, many of you have contributed actually to that. I hope I have acknowledged most of you. And so here I'm just going to review some of the results from my point of view. So from my perspective of, how can we make sense of these results? So one result which I think summarizes it well is this result that is in this paper by Song Mei, Theodore Misiakiewicz, and Andrea Montanari, that says that if your data is isotropic, so you can consider either uniformly on the sphere or Gaussian, as we are doing here, if you have number of samples and the number of hidden units which scales polynomially with the dimension, if the dimension is large enough, so the best thing you can do with a kernel method, and including the random features model, is to learn a polynomial approximation of your target function. So if you have a target function which has is a polynomial of like arbitrary degree, if you just have n and p proportional to d, you can only learn a linear approximation to the target function. To learn a quadratic approximation, you need n and p to go quadratically, and so on. So in some sense, kernel methods have this bottleneck that they can only learn a polynomial approximation if you just have polynomial sample complexity, and if they are expressive enough. So this essentially tells us that in the proportional regime that has also been mentioned here in previous talks, the best thing you can do to learn in your target function is going to be a linear function, plus the nonlinear part is going to be just behaving as additive noise that I can just include in the noise. And the intuition behind this result is very simple. Like if you decompose your nonlinear activation in the basis of orthogonal polynomials with respect to the measure of the data, so here is Gaussian, so that's going to be the Hermite polynomials, you're going to see that you can decompose into zeroth order terms, first order terms, and then higher order terms. And you can see that the higher order terms, since the Hermite of alpha is a polynomial of degree alpha, due to the scaling of the data, since I'm considering this high dimensional scaling, all of this is going to be subleading in terms of my generalization error. So you can make this formal by looking, let's say, like at the norm of the features. And this means that in the proportional regime, this feature map is going to behave like a linear map. And this means that this is why I can only learn the linear part of the target function. So yeah, these are the Hermite coefficients. So let's say in the proportional regime, that's the equivalent feature map. And this is what we call in the literature a Gaussian equivalence. It means that your model can be nonlinear, but in the end of the day, since you are in the proportional regime, your data is isotropic, it is just as if your map has the expressivity of a linear function. So this is very nice because we started with something nonlinear that we don't know how to do random matrix theory with, but then it's equivalent to a linear thing. This linear thing is Gaussian, so we are happy because we can do asymptotics and we can characterize the generalization error. And indeed, we did that, and we are not the only one to do that, but that's our way of writing this. If you just do the standard, kind of leave one out argument for deterministic equivalence and so on, that's the kind of formulas that you get for exactly characterizing the generalization error in the proportional limit. And then you can plot things, and you can get like double descent, and you are happy. Like you have a theory for, why overfitting can be benign in this type of models. However, there is a tight connection between being able to draw these curves and the first result that I gave to you. Actually, you can always see that if you have a Gaussian universality, you have equivalence to a linear model, and means that the best function you can learn, even at infinite width, as long as it's proportional to D, you can at best learn a linear approximation of your target. So there is this kind of yes, we are happy, we can draw these curves and we can make sense of stuff, but we are limited in expressivity, so Gaussian equivalence can be like either seen as a good thing or a bad thing. So that's my way of seeing all the results on the random features model. That's my perspective, is like, doing exact asymptotics require making sense of nonlinear functions, and the way to make sense is like expanding it, and expanding often means that you're gonna be only learning up to the expansion of the feature map. So just to give you a partial summary, if you didn't follow the maps until now, kernels and random features are able to learn anything, but they need a lot of data. They need polynomial data to learn a polynomial approximation. In particular, if you are in the proportional regime, which is going to be the topic of the rest of the talk, you can only learn a linear approximation. And the question we want to answer here is, okay, now if you train the first layer, like remember we were at initialization, random features model is equivalent to a neural network at initialization. What happens if we move away from initialization? What happens if you learn features? Can we do better than kernels? And that's kind of fundamental, right? Because if kernels can learn everything, you need to be comparing with respect to the performance of the kernel. So that comes to the main topic of the works that I want to present to you today, which is what happens when you do one step of gradient descent. So now we are going to consider taking the first layer weights and making one step, like a full batch step of gradient descent. And here we are going to be making approximation, which is some stuff wants to update. So my slides, I hope it doesn't ask again. Okay, so where I was? Okay, so we're going to be making this approximation on the training. So instead of training the first and second layer at the same time, which is what you usually do in your optimization algorithm, we are going to be making a two-step training procedure, which is convenient for theory, which is, okay, I'm going to make one step at my first layer weights, and then I'm going to train my second layer weights on the top of that. And I'm going to be asking, okay, can I do better than if I didn't do this step, meaning like eta equals to 0? Can we do better than learning a linear approximation of the target function? And we are going to be thinking about this proportional regime where n and p are proportional to d. So we were not the first one to think about this problem. Actually, two authors of this paper are here, like Danny and Zhishao, like that draw the attention that if you take the learning rate to be an order 1 quantity, you can still have some sort of Gaussian equivalence, meaning that your error improves, but it doesn't improve to be better than a linear approximation. So still the best linear method is going to be a bound for the performance. And actually, also they observed in this paper, they show that if you take a learning rate which is extensive in the dimension, then you can go below this line. But in the paper, they are not getting an exact asymptotic description of this curve. They are just showing that actually you can do better than a linear approximation of the target function. So here, essentially, you still have some Gaussian universality for learning rates which are order 1. Then you can do exact asymptotics. And if you go beyond that, it's a bit harder. And then you need something which is beyond Gaussian universality. Because, as I said, there is this tight connection between Gaussian universality and the performance being bounded by the best linear approximator. So this is like one result that we had in the first paper. Like, let's now consider like target functions which are functions of R directions. So this model appeared already in the previous talks. That's called the multi-index model. So that's a particular model that encodes this inductive bias that we have, that data might lie in a low-dimensional manifold, even though in RD you might think your data is spanning all the space. It's implicitly just depending on a few projections on a few directions, which I call here W1 star up to WR star. And here you're asking the question, for this multi-index model, how much data do I need to pick each of these directions? So here the idea is essentially the same. You can decompose your target function into a Hermite decomposition. Now this target function depends on R variables, so it's going to be a tensorial decomposition. And you're going to see that actually the difficulty of learning a certain target, like multi-index target function, if your data is isotropic, is going to be given by the first non-zero Hermite coefficient. And that's something that also appeared in Danny's talk before. So there are functions which are easier or harder depending on what is the first non-zero term in the expansion, in this tensor expansion in the Hermite basis. And essentially, the result we showed in this paper is that we can characterize what is the sample complexity, how many data you need in this first step in order to correlate the first layer weights with a subspace spanned by these directions. And essentially what you can show is that, so some of these results were known before, actually up to here was known before, then we extended to there in these two works. So essentially if you have less than linear sample complexity in the dimension, you cannot learn anything. Then here you can start learning one direction, and actually you can characterize which direction it is if you have n proportional to d. But to learn more than one direction, you need n to be proportional to some power of which is higher than d. So essentially, if you're just interested in proportional asymptotics, which is here, the best thing you can do is to learn a single, a nonlinear function of a single direction. And actually, I'm showing you plots because I come from physics. But if you like theorems, you have them. You can go to the paper, and you can have it. So essentially, to summarize what I think, my goal is not for you to parse this in this talk, right? If you want to learn more about it, go to the paper. But so what I want to tell you is that if you do a single gradient step, and if you're interested in learning nonlinear functions, if you are in the proportional learning regime where the quantity of data, the number of hidden units, and the learning rate are proportional to d, the best thing you can do is learn a nonlinear function of one direction. So I'm telling you that because now I'm gonna concentrate, I'm gonna focus for the rest of the talk in a target function which is a nonlinear function of a single direction. Remember, this is still better than the kernel because the kernel can at best learn a linear approximation. If g is nonlinear, the kernel is just gonna pick the linear part of this function, and then if you have linear sample complexity with one step, with learning rate proportional to d, you potentially can learn any nonlinear function of this direction. So there is this separation between neural networks and kernels in this regime. Can we get a sharp asymptotics of the generalization error? So that's the question I'm going to be interested in. Can I draw these double descent curves now for the learned features after one step? That's going to be my goal for the rest of the talk. So after a single gradient step, you can look that your weights look like that. That's just exactly rewriting the update of the gradient. Note that I changed my y by a g of this because that's the best I can do. Anything else would be just like noise. So drawing some inspiration from this work, you can decompose your weights into a part which is the initial weights, plus some rank 1 component, plus some correction. So this rewriting for now is exact. That's just the exact expression of how to make this decomposition. And for now, I'm gonna be focusing when my second layer weights during this first gradient step is all 1, and I'm gonna relax this later, and I'm gonna explain what changes in the analysis. But for now, bear with me with first layer weights. Second layer weights is initialized to all 1. And then the first thing you can do is that in the proportional regime, you can show that this correction that I said, so you have the bulk part plus a spike plus some correction. This correction just renormalizes your bulk. So you can show that this correction preserves the orthogonality of the weights at initialization, changes the norm, and makes it slightly different from the initial condition, but you can morally think as it still being a Gaussian matrix. It's not a Gaussian matrix. A Gaussian, this is going to depend on the details of the architecture, but you can morally think just for the sake. And that's what we call a spiked random features model. It's a random features model where the weights of the random features have now a spike. And these are the constants that characterize the magnitudes of the spike and the alignment of this spike with the target function. Because since now you took one step using data, this spike is going to have some correlation with the target, and this correlation can be asymptotically characterized. It's given by these functions, this expression, and this expression, of course, depends on the composition of the target function on the Hermite basis. And that's what we call a spiked random feature model. So here, we would like to do exact asymptotics. So we would like to characterize sharply what is the generalization error for this model in this regime. And if you pay attention in the first part of the talk, you know what we are looking for, right? We are looking for some sort of way of linearizing the nonlinear part of the random features model. So we are looking for some universality. We are not looking for Gaussian universality, because Gaussian universality would mean that we will be bounded in performance. We are looking for something that can capture the fact that now I have this spike, and this spike correlates with the target, and this means that I can obtain some nonlinear, I can learn a nonlinear function along the direction of the target. So we need to work a little bit harder than Gaussian equivalence. And if you do it, you see that you can derive a similar result. So this is the traditional Gaussian equivalence. You linearize the nonlinear function. We can have what we called a conditional Gaussian equivalence for this spike random features model. And then we are happy because we went back from something which is nonlinear to something which is linear on these weights. Now, the catch is that these coefficients now, which before were just the Hermite coefficients of the activation function, because the pre-activations were Gaussian, so you're just expanding the Hermite basis, now they depend on the spike. And in particular, they depend on the correlation between the spike and the data. So now we have these coefficients. They are not constants anymore. They are something that are functions of the correlation between your spike and the data. OK? And if you just get an example of an activation function, like the sine function, then you can compute these things. They're just functions of this kappa, kappa being this correlation between the spike and x. OK? With that, we can now do an exact characterization of the error. And so the main result is that if you now train the second layer, doing ridge regression on these features, on this spiked random feature model, which models the one gradient step, we can completely characterize the minimizer. And it's going to be given by some horrible expression as before, actually even more horrible, because now we have these spikes. And I can show you. It's like that. It's terrible. But OK, again, the goal is not to parse this. These are just, if you are into random matrix theory, you know that every time you have a random matrix theory result, you have some self-consistent equations that you have to solve. Here, there are two levels of deterministic equivalent, because there are randomness in x and randomness in the weights. And there are these spikes. You need to treat them exactly, and they give you something horrible. But OK, the partial summary is that if you do a single step of gradient descent, you can approximate this by a spiked random features model. You can use and you can prove a conditional Gaussian equivalence, which allows you to handle the nonlinearity. And this allows you to give a sharp asymptotic description of the generalization error, of the minimizer, of doing ridge regression on the features after this one step. Remember, we are always separating the training procedure in two steps. First, one step in W, then training A, or the second layer, to optimality. OK? The formula is horrible, but we have plots. So again, like if you have dots, dots are like finite size experiments. The curves are the theory, solving these saddle point equations. And here you can already see some interesting phenomenology. So if we go back to this plot about the performance against the best linear predictor, you can see that if you use enough data in your first step, then the features that you learn allow you to learn better than a linear approximation of the target. So you can cross this line here. That's nice. And you can see that it's kind of intuitive. The more data you have, the better performance you get. So from these formulas for the generalization error, you can also get some intuition about the spectral properties of the model. So you can also see how the bulk changes. As I said before, a key component of this result is that you need to control how the bulk changes after this one step. So here it's the bulk at initialization, and here is the bulk after one step. And you can see that it's developing these tails. And I think this also kind of resonates to the talk this morning about the effect of training on the spectrum, like the empirical covariance of your features. And here is one example. It's a simple example. We are making a lot of assumptions, but it's one example we can exactly characterize what's going on the features after this gradient step. So that's nice. And of course, there are the spikes that you need to control that are not plotted here. So what else can you say? So if you are like more on the statistical learning theory side, you say, oh, your formulas, they are big, and I cannot make sense of that. And this is horrible. Give me bounds. OK? We can try to give you bounds. If you look at the exact generalization error, I mean, it's kind of a pity, right? Because we have the exact description. So we're going something exact to something which is an inequality. But anyway, here they are. If you look at the error looks like that. And you can then make some simplification, get rid of some terms, and derive some upper and lower bounds of how does the error depends on these like conditional Hermite coefficients. So for instance, here you can get like a low dimensional description of what sort of functions are being spun by your features after this gradient step. So remember that g of kappa, that's your target function. And effectively, you can show that your generalization error is lower bounded by this square error in a one-dimensional space. Now you got rid of high dimensionality. You took the limits. And you can see that, what you need for this to be low, you need this mu0 of kappa and mu1 of kappa to be as low as possible, which means that it needs to approximate well this function g. And then you can try to ask yourself, OK, when does this spans this function g so that the error goes as close as possible to 0? And you can also plot, since this is a one-dimensional function, you can also plot, like, let's say here you have your target function, some kind of a sinusoidal. And then you can plot like the lower bound and the upper bound given by the exact generalization formula. So you can also start thinking about function approximation results of what is being learned after this one step. So that's quite nice. And in particular, you note that this quantity is there. This is the L2 distance with respect to the Gaussian measure between your target function and the span of these two functions. That depends on your activation function. So you can start thinking about what are good choice of activation functions to be able to approximate a given g. And you can make these bounds a little bit tighter by optimizing over the learning rate. Because this, of course, all of that depends on the learning rate, which is the size of your step. Here, I'm always taking a step which is order d. So it's always an extensive step. But there is a constant. And you can optimize over this constant. OK, so let me just now give two notes. One note about initialization. So I said that I took this second layer weight, to be all 1. What does it change if I take it something to be on a finite alphabet? So I initialize like taking my second layer weights randomly from some finite alphabet. Then what happens is that these functions, mu1 and mu0 that appeared in your bound, now becomes a function of the alphabet times kappa. So you can see this is like an effective single neuron with random weights. And then you can see that the more expressive the features are going to be depends on the variability you have on the second layer weights. So the more variability in your initialization, the more likely you're going to be able to span a richer space with your features after one step. And you can plot this thing. So for example, here you have an alphabet of 1, which is like the all ones. then let's say an alphabet of size 2, an alphabet of size 3, and you can see the performance improving as you increase the alphabet. Of course, the details are going to depend on your target function and on your architecture. So let me also comment on some related work. So a little bit before our paper went out, so there was this nice contribution by the group of Edgar Dobryban, who studied exactly the exact asymptotics, but in a complementary regime. So instead of taking the learning rate to be the critical one, which is proportional to the dimension, they studied the learning rate, anything between being like constant, which is the case studied in the paper that I mentioned previously, and a learning rate that scales with the dimension, but between 1/2 and 1. And what they can show is that in this regime, you can obtain some nonlinear approximation of your target function, but you'll never be able to exactly learn the full nonlinear function. So yeah, if you're also interested in that, I recommend taking a look at this paper because it's kind of complementary to ours. We look at the critical learning rate regime where you can learn any nonlinear function in the direction of the spike. They learn, they look at the intermediate learning, like the first paper that inspired this line of work looked at the constant learning rate regime, and they looked into the intermediate learning rate regime as you can learn higher and higher order polynomials of the target function along the spike, and these higher orders are related to the control of the spikes that get out of the bulk after initialization. Okay, so before finishing, I'd just like to give you a couple of ideas of the random matrix theory proof. So I'm not going to be very formal here, but there are essentially two steps in the proof. The first one is that you start with your exact features, which is the feature, the nonlinearity applied to the one-step weights times your data. The first step is that you want to approximate this by spike random features model. So here I put a warning, because when we started working on that, we thought that this approximation in the proportional regime was exact. It turns out that it's not exact. Actually, these spikes in the other paper that get out of the bulk, as you increase your learning rate, they accumulate and accumulate, and they renormalize your bulk. So you need to have a tight control of your bulk. So even if you start with a Gaussian matrix, if you take a learning rate which is proportional to d, what happens is that your bulk gets deformed and is not a Gaussian matrix anymore. It is still approximately orthogonal, and you still can control the norm. So it means that you have to work harder. It's just not like a Gaussian matrix with a different norm. It is now something else, which is a matrix with approximate orthogonality between the rows, and you need to work harder. But we thought this, and actually in all the plots that I showed you, they are the exact spike. So it also depends on the nonlinearity, and it's hard to see this, but we can construct some examples where you can actually see the difference between keeping the initialization Wishart and exactly accounting after the one step. So you need to be careful. But if you are careful, then once you have the spike random features model, then you have to prove a conditional Gaussian equivalence to linearize sigma. Once you have that, you have to do random matrix theory, because now you have the empirical covariance of the features. And essentially here, just the standard random matrix theory you do. You do 2 stages of deterministic equivalent to get rid of the randomness of both the data, x, and of the bulk, w tilde. And this just leave one out and some Burkholder inequalities. And here the main challenges are that in the features you need to control the k spikes separately. The k is the size of the alphabet of the initialization of the second layer. So you need to separate the features into spikes and something that you need to treat separately. And for the bulk, you need to derive some deterministic equivalence for some block-structured Wishart matrices, which, as far as we know, we couldn't find in the literature. So if you know something like that, like deterministic equivalence for this type of matrices, like here, Wishart product-wise with this type of block matrices, let me know. I'll be interested to discuss. And with that, I see you already here. Let me just conclude. In the proportional asymptotics, kernels can learn at best a linear approximation. With one gradient step, two-layer neural networks can do better than kernels along one and only one direction. And we can provide a sharp asymptotic description of what is learned and how well is learned, because it's exact. So there are many open directions. Let me thank the collaborators that appeared in these works that I've presented here today. And thank you for the attention.
I think we have like time for maybe 1 or 2 questions. Anyone have any questions? Oh, if not, wait, we have 1 more speaker. And if not, we'll get to the next speaker.
Yeah.
Thank you. Thank you, Bruno.